Hello and what's up, everybody? Today we are going over the lesson proof positive, and we are taking our first look at what we call formal proofs. I've talked about this multiple times this year already, and said that we're going to get to this point where we prove things to be true, right? And you have your reason, you have your statements, and you have your reasons. And we kind of talked about this a little bit last week, and I did some demonstrations of this a little bit last week. So now it's just going on top of it, right? So now we're looking at actually formal proofs. But to start off, we need to come up with some reasons that we could use, right? So during this lesson, we're going to be looking at recognizing postulates as building blocks of proofs. We talked about postulates in the past. Postulates are little facts, right? That we all believe to be true, even though you can't formally prove them to be true. For instance, all right angles are 90-degree angles. We know that those are true, but we can't necessarily prove that to be true, right? Next up, apply real number properties to angle measures, line segments, and distances. Prove theorems involving angles, and complete a flowchart proof. So first up, it says you previously made, let me cut off and rewind a little bit. This is on page M262. If you're taking notes in your book, this is on page M262. I will have all the pages down at the bottom of the screen so you could just stay in line, right? So this one says you previously made conjectures about the sum of angle measures of the measure of two angles and two arcs. These conjectures are actually postulates. You were introduced to the following postulate in previous topics, blah, 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 right? And we have three different postulates. We have our angle addition postulate. Basically, it says if you add two angles, they create a bigger angle. Our linear pair postulate that says if two angles form a linear pair, then they're supplementary, which means that they add up to 180. And you have your segment addition postulate, which basically says if two segments are added together, they create a bigger segment. Nice and simple, right? So these are going to be important. Make sure you keep this little table in mind when we come to future points, or you might have to look these up every now and again, right? So let's just jump into actually doing some stuff, right? So I want to write examples for each of these little properties and postulates and things that we have here, right? So this is on page M263, and we're going to follow along and we're going to write examples. This is give algebraic examples of each property using numbers and variables. So my addition property of equality, all this basically says is if A, B, and C are real numbers and A equals B, then A plus C equals B plus C, right? So what does this mean, right? So you could do this with other variables. For instance, an example would be if we have X equals Y, we could then say that X plus Z equals Y plus Z. But if we want to look at this as like numbers, right? So one thing we could think about is we could say that 2 is equal to 4 over 2, right? This is just one way to visualize things. 4 divided by 2 does equal 2, right? So we could really write this as 2 plus 3 equals 4 over 2 plus 3. And it means the same thing. Or in other words, if you add something to both sides, it's still going to be true, right? It's still going to be true. So we added 3 to both sides and they're still equal, right? Because they were equal to begin with. Our subtraction, it's the same thing, right? So if we have X equals Y, we could say X minus Y, X minus Z equals Y minus Z. Same thing. If you subtract something from both sides, the two things will stay equal because you're taking away the same amount from both sides of this equation or whatever we have going on here. Next up is our reflexive property. Basically, something is equal to itself, right? So we could say that angle X, Y, Z is equal to angle Z, Y, X. They're still the same angle. They're just named differently. P equals P. Something is equal to itself, right? Or even 5 is equal to 5, right? That's all our reflexive property is. It means that something is just, it's equal to itself, right? My right hand is equal to my right hand. My left hand is equal to my left hand, so on and so forth. And next up is our substitution property. It says if A and B are real numbers and A equals B, then A can be substituted for B. And we've done this. You've done this multiple times with like equations, right? So for instance, if we have an equation and it says 3x plus 5 equals 18, or maybe not 18, right? 3x plus 5, right? Say we have this expression here. And then we say, well, x is equal to 4. We could substitute this in. So instead of having my x here, we could write 3 times 4 plus 5. And that is our substitution property. So whenever you swap things out like that, it's our substitution property. And last but not least, our transitive property. This one says if two things are equal to the same thing, then those things have to be equal, right? So it says if A, B, and C are real numbers, A equals B and B equals C, then A equals C, right? In other words, let's say we have something, we say that AB is equal to CD and CD is equal to EF. That means that AB has to be equal to EF. Basically what it means, right? And these are a bunch of properties. Once again, this is a good page to kind of like make sure you remember where it is, where it's located, so that you could just go to it and use it as examples, because you're going to have these in math here. You're going to have these on practice problems and assignments, right? And you're going to be able to pull them up and be like, hey, what is the reflexive property again? Or what is the subtraction property? Having examples written out will really help you locate it and identify what words go with what idea, right? So next up, it says consider each diagram and write a statement that applies to the property to angle measures, right? So we have a situation here and we want to write an example of the subtraction property of equality. This is on page M264. So subtraction property of equality. Basically, we're going to take a bigger angle and we're going to subtract and we're going to get a smaller angle. Basically, that's it. Or we could say we have two different angles and we subtract things from them and it gives us the same angle. So for instance, we could say that angle AEB, which is this small angle here, is equal to angle AEC minus angle BEC. Basically, that's it. Right? So another example of this could be something like this, where we say if AEC is equal to angle BED, then we could say AEC minus BEC is equal to angle BED minus angle BEC. So basically, the bigger angles, and then we subtract that same smaller angle away from both of them, should be equal, if those bigger angles are equal. Next up, our reflexive property. Very simple. This one's going to be dumb easy, right? Something is equal to itself. That's what the reflexive property means. Our something here is angle A. So we could say angle A is equal to angle A. Bing, bang, boom, done, easy. Just this angle is equal to itself, right? That's it. Next up, the substitution property. So for this one, we could say if angle A is equal to 90 degrees, right? Angle B is equal to 90 degrees. Then, actually, this is my transitive. Whoops. Messed up my substitution and transitive. I apologize. Right? We could say that both of these are right angles. So angle A is equal to 90 degrees. Therefore, angle B is equal to 90 degrees. We substitute A out for B. Nice and simple, plain and easy. Transitive property is this one, right? So we could say that angle A is equal to angle B, but we also know that angle B and angle C are equal, which would then mean that A and C also have to be equal, right? So if two things are equal to the same thing, then those things have to be equal, right? Just like if let's say two people were the same height, and then one of those people is the same height of someone else, then the other two people are the same height, right? You could do this with a bunch of different things. So our subtraction property of equality. For this one, we could say that but now we're using segments. We're saying AC is equal to BD, right? But then we could say that AC minus BC is equal to BD minus BC, right? Since AC and BD were equal to begin with, when we subtract the same thing away from them, they stay equal to one another. That's our subtraction property of equality. Next up, reflexive property. Once again, our reflexive property means that something is equal to itself. So we could say CD is equal to CD. Nice and easy, plain and simple. Nothing really hard there to work off of. Our substitution property, right? We could say CD is equal to 8, but we also know that EF is equal to 8, so we could say CD is equal to EF, right? Easy there too. Or you could do this in the opposite order, right? CD is equal to EF, therefore CD is equal to 8. Same thing. Transitive property, right? Two things are equal to the same thing, right? So we could say these are equal and these are equal, right? So let's say MN is equal to WX, but then we also know that RT is equal to WX. So what could we say? We could say that MN is equal to RT. Nice and simple. Using these properties, right? And this is our transitive property. So now that we have these properties in mind, we can start thinking about proofs. And what will proofs look like, right? So a proof is a logical series of statements corresponding with reasons, right? So if you make a statement, right, it's always giving that reason to back it up, aka that why, right? So let's see what that actually means. So in proofs, you always have a given and something you need to prove, right? So we could always write these out of conditional statements too. So our first one says if the measure of DEG plus the measure of GEF equals 180, if angle DEG and angle GEF are a linear pair. So what do we want to, what's our given, right? It's saying, well, if this is a linear pair, so that's our given. So angle DEG, and GEF are a linear, whoa, my handwriting is sloppy, pair, right? And then what do we want to prove? Well, we want to prove then that they equal 180, that first part of this statement. So usually your if section of these statements are going to be your given. Because we're thinking like, hey, if this is true, therefore it's given to us that it's true. So for my next one, it says if angle ABD and angle DBC are complementary, then BA is perpendicular to BC. So once again, our given is that if section. Now it's up at front. So we could say angle ABD and angle DBC are complementary. Another way to think about this is angle ABD, or the measure of angle ABD plus measure of angle DBC equals 90. That's what complementary means, right? This means then what we're trying to prove is BA is perpendicular. That's what that upside down T means. BC. That's what that means right there. So that's what we're trying to prove. So we wrote out our given, it's that first section, and then we wrote out our proof. And remember, these two statements are equal. They're equal. They mean the same thing. So next up, it says if angle 2 and angle 3 are vertical angles, then 2 is congruent to 3. So once again, our if is angle 2 and angle 3 are vertical angles. So then our proof is angle 2 is congruent to angle 3. In order to prove, we need to prove that to be true, right? So you always start out with this given, you always have a goal. Your goal is what you want to prove. So that's how it works. One way we do this and one way we organize it is called a flowchart. A flowchart proof is a proof in which the statement and reason for each step are written in boxes, and then we use arrows to connect the boxes and indicate how each step and reason is generated from one another, right? So here is an example of a flowchart proof, and I'm going to read through it and kind of explain all the reasoning, right? So first up, let's read our top text at the top. You can complete a flowchart proof of a conditional statement. So it says if AB is congruent to CD. This is our given, right? It's our given. And then AC is congruent to BD. And that's what we want to prove. Now, if you notice in step 1, it says AB is congruent to CD, and then it gives you the reason underneath it. And our reason underneath is given. You can use given as a reason. But if we scroll all the way to the end, we notice it says AC and BD. That's what we want it to prove. But is that a reason? No. Writing prove as a reason doesn't make any sense, right? Prove is something, it's a verb. It's something we need to do. It's not a reason to support things, right? You can't support yourself with, hey, well, prove. That doesn't make sense. So let's read through this and actually see what's going on. So they say AB is congruent to CD. Then we go down to step 2. Then they say the measure of AB is equal to the measure of CD. And the reason why is that's the definition of congruent segments. So basically what they're saying is, since these are congruent, we know that their measures are equal, right? They then say over here that we have BC is congruent or equal to BC, which means that that's the reflexive property. Something is equal to itself. They add BC to both sides of our previous statement, AB equals CD. So now we have AB plus BC equals CD plus BC. For 5 and 6, we say that AB plus BC just means it's AC, right? AB plus BC, that equals AC. That's our segment addition postulate. And then BC plus CD is equal to BD. So basically, this first chunk is equal to AC, and this second chunk here is equal to BD. So basically, if I change colors here, right? Oh, can't do that with my pen. Right, so let's say we go to green. Right, this turns into this, and then here we get this section turns into that, right? We're substituting it in because of the 5 and 6 right here. So finally, since the measures of those two are equal, we could write that they are congruent due to the definition of congruence, right? And once again, these are something that take practice and seeing them over and over again. It's exposure to these proofs that will make you comfortable with them. When you first start out and in the beginning, there's no way you're going to be comfortable with them, right? Looking at it right now, you're probably like, what the hell is going on? But the more you do and the more you see it, the easier they become, right? So let's just keep exposing ourselves to them. So now we're just going to kind of break this down a little more, but with explicit questions. This is on page M268, by the way. So it says, why is step 2 of the flowchart proof critical in getting from the hypothesis to the conclusion? So step 2 is right here. That's what we're focusing on. Why is this a critical step? Well, because when we are adding and subtracting segments to each other, that's when we have to make it an equal sign and not a congruent. This is just like a formality, right? So why is this critical? We need, oh, my handwriting is so sloppy today. I apologize. We need equal signs to add segments, which we do in the next line. We add segments, so you need the equal sign. You can't add the segments with congruent signs. It's just a formality of writing things in geometry, right? So you need to use the equal sign in order to add things there. So that's why that step 2 is important. Next up, why does step 8 follow step 7, right? So 7, 8 right here. So it says, why does 8 follow 7? Why does it go this way and not the other way? Well, because our end goal and what we want to prove, we look all the way up at the top where it says, then ACE is congruent to BD. That has to be the last statement of our proof, right? Whatever you're trying to prove has to be that last statement. So step 8 has to be the last statement due to it being what we want it to prove. There we go. So it has to be the last one because that's what we want it to prove. So it needs to come all the way at the end. Awesome, awesome, awesome. Moving forward. Is there more than one correct way to order these statements of reasons? Explain your reasoning. The answer is yes, right? So for instance, one way we could do this is if we switched, sorry, not 3. We switched 5 and 6. That would be the same thing, right? You could also switch 2 and 3, right? These would all work. And I'm not going to write this all over here, but even if we switch those, it wouldn't necessarily mess up the proof. The main reason for this question right here is to say sometimes your proofs are going to look a little different than mine or your classmates or something like that, or they might be in a little different orders. That's okay, right? They don't always have to be in the same exact order, just as long as you get necessary steps. Now, some steps do need to be in the same order, but other steps maybe not, right? So basically, that's about it. Next, a 2-column proof is a proof in which the steps are written in the left column and the corresponding reasons are written in the right column. Now, these are the proofs that I learned when I was younger. They never showed us flowchart proofs. They showed us 2-column proofs. I like it because it appeals to me being all organized, right? So flowcharts, there's like boxes and lines, but in 2 columns, you just have your steps and your reasons, right? AKA your statements and your like why, right? Your reasons. And so you write your statements here and then you write your why next to it. So statement 1, why 1, statement 2, why 2, right? Or the reason. And this is the same one as we just did in our last one, but basically it's just a more organized, like formal way to write these proofs. So how do 2-column proof relate to the flowchart proof? They are the same, just look different. So what does that mean? They do the same thing, but they just kind of look different. They're organized different. They're packaged differently if we want to think of it that way, right? So they're the same, they just look different. And last thing we want to do today is just actually try to fill in some things with this proof, right? So here it says complete the flowchart proof, and this is on M270, right? So complete the flowchart proof of the right angle congruent postulate by selecting the reasons from the word bank for each statement shown and writing it in the correct step. Now, once again, I'm going to make this look super easy because I've done this, right? I've done this for years. I learned it in high school. I learned it in college, and then I've taught it. When I learned this in high school, it was so hard for me, right? So don't be discouraged if you struggle with it. But guess what? The more I worked with it in high school, the better I got. And then I worked with it more in college and I got even better. And now I teach it and it just comes naturally to me. I could see things and I'm like, oh, this is that, so on, so forth, right? So let's look at let's start all the way on the left here. And you want to look at your diagram, right? So we have some angles and we have what looks like two lines, or a ray and a line that looks like they're going to create a right angle, right? And then we look at our given and our prove. So where we're starting and where do we want to go, right? So this is the start. That's the way I like to think about it. And this is the finish, right? Let me erase that and write. This is the finish, right? So it's like a race or like a path that you want to get to, or a hike, right? You have your start and you have your finish, and you have things in between that you need to get through, right? So our start says angle ACD and BCD are right angles. So what I'm going to do is I'm going to mark that off. Boom. This is a right angle. That's a right angle. And what do we want to prove? We want to prove that ACD is equal to BCD. Super simple. This is a very simple proof. So let's look at up top. It says angle ACD is a right angle, which is what we have right here. ACD is a right angle. But what else is a right angle? It says BCD is a right angle. What was our reason for ACD being a right angle? It was given. It was told to us, right? So whoever wrote this problem said, I know this is true. So here's that information. I'm giving it to you. So why is BCD a right angle? For the same reason. It's given to us, right? And there's in our bank, our reasons bank, it's right there. So we're going to get rid of that one. The next up, it says the measure of angle ACD is equal to 90 degrees. And why? That's the definition of a right angle. So we said right above it that ACD is a right angle. What does that mean? That means it's 90 degrees. So we write that it's equal to 90 degrees. Why? Because it's the definition of a right angle. And if we look next to it, it's the same thing, right? But just different angle. So it says BCD is 90 degrees. Well, why? Same reason. I'm going to abbreviate it. Def of right angle. That's my angle symbol right there. So definition of right angle. Right here, and we cross that reason off. Now we say that they're equal to one another. Well, why are they equal? Well, and what are we saying is equal? We could say that the measure of angle ACD is equal to the measure of angle BCD. And why are they equal? Because they're both equal to 90, right? They're both equal to 90. So this is our transitive property. That's our transitive property right there. So last but not least, we say instead of having the equal sign here, we switch it to a congruent sign. We get rid of the little m for measure. So now instead of saying measure of angle ACD is equal to measure of angle BCD, we're saying that angle ACD is congruent to angle BCD. Why? This is our definition. Once again, I'm going to abbreviate it. Def of, and instead of right incongruent, I'm going to do the little symbol. This is our definition of congruent, angles. Definition of congruent angles. Our last reason right there, and we could cross that one off now. And there we go. We filled everything in using our reasons, and we completed our first little fill-in proof right here, right? Once again, I know this is going to be overwhelming. This is a lot of new knowledge, but this is what notes are for, right? You're not supposed to know something right away, right? You're not going to be masters at this right away. It's going to take practice and you actually trying and getting things wrong and then being like, oh, I recognize why I got this wrong, and practicing it in order to get better at it, right? So with that said, you guys are going to move to some practice, get some practice in. I wish you luck. If you have questions, comments, or concerns, please let me know. But if not, and you're good to go, awesome. Have a great day. And until next time, peace out, everybody.